have been discussing about problems concerning first law of thermodynamics, where the situation demands addressing unsteady state problems. We have worked out 2 problems so far, and we will continue with the next problem. So, this problem is a 1 meter cube tank contains ammonia at 150 kilopascal 25 degree centigrade. Okay. The tank is attached to a line flowing ammonia at 1200 kilopascal and 60 degree centigrade. The valve is opened and mass flows in until the tank is half full of liquid by volume, okay, at 25 degree centigrade. Calculate the heat transferred from the tank during the process. So, this is also a tank filling problem. We had solved one tank filling problem earlier. The basic difference between that problem and this problem is that that problem was pertaining to an ideal gas, and now we are trying to work out a problem which for a substance which is a phase changing substance. So, the methodology in which we solve the problem, although the concept remains very similar, but the methodology will be a little bit different, and I want to impose on you the very striking difference of solving an ideal gas problem versus a phase changing substance problem, because many times students who are confused between these two, and typically in the school level you have done mostly ideal gas problems. So, you have a tendency to use ideal gas concepts even for substances that are phase changing substances and so on. So, that should not be done, and this is an example where in such problems how do you solve. So, let me go to the board. So, you have a 1 meter cube tank, it contains ammonia V is equal to 1 meter cube, state 1 150 kPa 25 degree centigrade. Okay. So, this is connected to a supply line. So, there is a supply I, state I 1200 kilopascal, (60 degree centigrade). State 2 25 degree centigrade, and Vf is equal to Vg. Okay. So, that is the tank is half full of liquid, that means remaining half is vapor. So, volume of fluid and volume of liquid and volume of vapor are the same. So, and temperature is 20 degree centigrade. So, you have to find out the heat transfer, right. So, you write first of all mass balance. So, in this mass balance what you require is to use this equation. There is no exit, right, it is a tank filling problem. But there is M2 and M1, right, the tank was not initially evacuated. So, M2 minus M1 is equal to Mi. Then the first law for US UF Q okay. So, I have just written the full equation because if you start with the full equation and then put your constraints given data in the problem, that gives you a clarity of what you know, what you do not know, what you need to find out and all these things. So, first of all there is no work done, work done remains 0, then you do not have any exit state, therefore, this is 0. You will have negligible changes in kinetic energy and potential energy. For most of the problems it is like that, but I tell you, sometimes your examiner tries to make sure whether you are very alert. In some problems kinetic and potential energy changes may be important. So, you look into the problem statement first and see whether there is any hint that some of those terms may be important, check it very clearly. If there is no hint like that, you can safely neglect changes in kinetic energy and potential energy. So, you will have Q is equal to M2 U2 minus M1 U1 minus Mi Hi, Mi is M2 minus M1. Okay. So, this is M2 into U2 minus Hi minus M1 into U1 minus Hi, right. So, let us see what we know out of this. So, at state 1 temperature, pressure both are given. So, from here you can find out at state 1 what is required. U1 from the table you can get ammonia table, right, ammonia table, fluid is ammonia. So, do not this is again a very common tendency, because most of the times you are working with water, you have a tendency to jump into the steam table, although the fluid is not water. So, look into what is the fluid, enter into the corresponding table to get this. So, identify the state, get U1, and you also require specific volume at state 1 because you require mass. So, these two you get from table. So, mass is volume by specific volume, right. State 2, state 2, clearly you have a liquid vapor mixture, that means in the it is in the two phase region. So, you find out what is Vf at state 2, Vf at 25 degree centigrade, again from table. You also find out what is Vg, what is the mass of the vapor. See, here you have to use the basic definition of specific volume. So, mass of vapor is Vf by Vf by Vf2. What is this Vf? See, it is half liquid and half vapor. So, if total is 1 meter cube, this is half a meter cube, right. And this is Mf2, and what is Mg2? This is Vg by Vg2. So, this is and Vg2 is, you get from the table. So, you know what is Mf2 and Mg2. So, what is M2? Right. Not only that, you can find out what is the quality at state 2. What is that? Mass of vapor by total mass, right. Why do you require quality? You require quality because you have to know what is U2. So, U2 is 1 minus x2 UF2 plus x2 into Ug2. These UF2 and Ug2 are from table. Properties of ammonia at 25 degree centigrade. Okay. Hi in this equation, state I is given in terms of pressure and temperatures. So, you get Hi from 1200 kPa 60 degree centigrade. Okay. So, with all these if you substitute, you will get the total heat transfer, and this is the answer to this problem is minus 379.636 kilojoule. Okay. So, again you see that there is a heat transfer which is required from the control volume to the surrounding, because you are energizing the fluid more by supplying the flow energy or flow work. So, that energy somehow has to be dissipated through heat transfer to the surrounding. That is why this is a negative heat transfer. So, all these are very important. So, why you can say that well the answer is coming negative, so I understand this. Why this understanding is required? This understanding is required because say you are solving a problem, somehow this sign of this has not come correctly. That will give you a first check that the sign of either heat or work is not coming consistent with the physics of the problem. That should give you an alert. If you do not get that alert, that means you are dumb, you are just putting values and whatever is coming you are accepting it. So, you get an alert and based on that alert you figure out that whether it is consistent with the physical situation or not. If it is consistent with the physical situation, that does not essentially mean that your problem solving is correct, but if it is not consistent with the physical situation, it is definitely true that your problem solving is not correct. So, I would say that always be driven by these physics based considerations to put some basic checks on your answer. Okay. So, we will work out another problem. Let me erase the board. So, the next problem, problem number 12. So, this is a bit involved problem for the beginners. I would try to go through the problem very carefully. A steam engine based on a turbine is shown in the figure. So, what is happening is that there is a boiler. In the boiler, liquid water is converted into water vapor and then the water vapor is supplied to a turbine. So, the water vapor has high thermal energy. In the turbine, that thermal energy is utilized to do some work. Okay. So, this is the basic arrangement. So, you can see that in the schematic there is a boiler and there is a turbine and there is a pressure regulating valve that controls the flow from the boiler to the turbine. The boiler has a tank of volume 100 liter and initially contains saturated liquid with a very small amount of vapor at 100 kPa. Heat is now added by the burner. The pressure regulator which keeps the pressure constant does not open before the boiler pressure reaches 700 kilopascal. So, when the pressure regulator opens, the pressure is already 700 kilopascal in the boiler. The saturated vapor at 700 kilopascal enters the turbine and is discharged to the atmosphere as saturated vapor at 100 kilopascal. The burner is turned off when no more liquid is present in the boiler. Okay. Find the total turbine work and the total heat transfer to the boiler for this process. Okay. So, let me draw the schematic of this problem in the board. So, this boiler I am just drawing a block, there is a valve here and then it enters the turbine. Okay. So, this is turbine. So, to work out this problem, I would prefer to break it into two simpler problems. One is a control volume 1 which is around the boiler, this is control volume number 1, and another control volume number 2 which is the around the turbine. So, we will see what is happening around the control volume 1 first. The control volume 1 has volume equal to 100 liter, state 1 100 kilopascal saturated liquid, quality equal to 0. Okay. State 2, (700 kilopascal), quality equal to 1, saturated vapor, right. Then state E, what is state E? This is the exit state E. State E, 700 kilopascal, quality equal to 1, because now everything is saturated vapor and that only gets transmitted through the line. So, this is from the physical understanding of the problem. Okay. Now, for the control volume 1, let us apply mass balance and energy balance. So, M2 minus M1 is equal to Mi minus Me. So, here there is no inlet and there is exit. So, M2 minus M1 is minus Me. So, if we know what is M2 and what is M1, you can calculate what is Me. So, how do you calculate what is M1? So, state 1, specific volume is Vf1 at 100 kPa. M1 is V1 by V1. V1 is this 100 liter, this is same as V2. What is V2? Small V2, this is Vg at 700 kilopascal. Okay. So, M2 is equal to V2, which is again 100 liter. So, remember from liter, 1 liter is 10 to the power minus 3 meter cube. So, you have to convert that to meter cube by V2. Okay. So, you can calculate what is Me. Now, you apply the first law for US UF. Okay. So, now let us see what are the values. So, Mi, this is 0. Again, you know, for boiler kinetic energy and potential energy changes are not negligible, thermal energy are negligible and thermal energy changes are more important. There is no work done for boiler. So, Q becomes MEHE plus M2U2 minus M1U1, right. HE is what? HE is Hg at 700 kilopascal. Okay. So, if you substitute all those values, Q will be 224.9 megajoule. Okay. So, this heat transfer is required for many things. One is converting the water to liquid water to vapor water. Next is supplying additional energy so that there is a flow energy that is created and that vapor flows across this. So, these two forms of energy, that energization is reflected by this heat transfer. So, the next is the turbine work that we need to convert. So, we will next consider the control volume 2, which is the turbine. So, for the control volume 2, let this I dash is the new inlet state, which is same as E, at least for enthalpy, not for everything else, but we require only the enthalpy. So, M I dash will be equal to M E, right. For the turbine, let us write this. So, this is a general law, you can apply it for steady, unsteady, whatever. So, let us apply this Q plus M I prime new state I prime into H I prime plus V I prime square by 2 plus G Z I prime is equal to M E prime H, this is E prime, H E prime plus V E prime square by 2 plus G Z prime plus M 2 into something minus M 1 into something M 2 prime M 1 prime plus W, very important. This is the purpose of the turbine, to get work done. So, now one physical understanding that you have, that you must have, is that the turbine is a steady state device. So, because turbine is a steady state device, the state of the fluid in the turbine does not change with time. So, these state and these two energies are the same. This is a physical understanding about the operation of the turbine you must have, to solve this problem. So, this change is 0. Turbine is primarily for work done, heat transfer is neglected until and unless. So, this is approximately 0, not really, but as compared to this is not very significant. You can neglect the changes in kinetic and potential energy. If you do that, then W will be M I prime into H I, so prime minus H E prime. So, state E prime is given. So, E prime is 100 kilopascal and quality equal to 1, saturated vapor. Okay. So, M I prime is M E for control volume 1, this you know, and H I prime is H E for control volume 1, that also you know. So, if you know these two and this you get from the table, 100 kPa quality equal to 1. So, table. So, that makes you have all the data that is required to calculate the work done, and this is 8405 kilojoule. Okay. So, this is the total turbine work for the heat that is supplied by the boiler. Thank you very much. We will continue again in the next lecture.